Hello everyone and welcome to this talk where we'll give an ideal explanation as to why some codes achieve the so-called list decoding capacity. I am Siddharth at TIFA Mumbai and this is work with Prahlad also at TIFA, Mrinal at IIT Powai and Madhu at Harvard. Let us now look at some popular codes and their list decoding abilities. The most popular family of codes arguably is the Reed-Solomon family of codes, and in a famous work of Guruswami and Sudan, they were shown to be efficiently list decodable up to the so-called Johnson radius. We will later see in a bit what list decoding is about, but this is just to put our result in context. The now popular folded Reed-Solomon family of codes were the first family of codes to be shown to be efficiently list decodable up to the capacity in the work of Guruswami and Rudra. What this essentially means is that you can produce a small list of code words given a corrupted word where the number of corruptions is slightly shorter than the distance of the code. The next family of codes which was shown to achieve this list decoding capacity are the multiplicity codes, where along with the polynomials evaluation you also give its derivatives. And then there are the lesser known family of additive folded Reed-Solomon codes, where the folding, as opposed to folded Reed-Solomon codes having a multiplicative folding, these have an additive folding, and they were also known to achieve the list decoding capacity efficiently. So the question then becomes that all these codes that we just saw are sort of a bundling up of the Reed-Solomon codes, and the alphabet increases by the amount you want to bundle. But this harmless looking operation somehow leads to these codes being efficiently list decodable. And our work tries to explain, or at least give a unified explanation as to why this bundling seems to work, and are there other kind of bundling patterns which would have worked. Because in folded Reed-Solomon codes you bundle uh, the various multiplicative shifts applied to a polynomial. In additive folded Reed-Solomon codes you bundle various additive shifts applied to a polynomial. In multiplicity codes you bundle various derivatives of the polynomial. So we try to give a unified explanation of why this bundling seem to work. Now let's move on to a primer on list decoding, a very quick one. So we will exclusively work with linear codes in this talk. So script C is the code residing in f to the n, where f is field and n is the block length. It is a subspace of dimension k, and the distance is just defined as the minimum Hamming distance between two distinct code words fractionally. Since it's a linear code, you might as well assume p is 0 in the definition, and the rate is just the dimension by n. And what is the question of unique decoding? Question of unique decoding then says that given a received word w, can you find all code words in script C such that they are within a ball of delta by 2 around w? Okay. Of course, there can only be one such code word, because if there are two such code words, let's say p is a code word and p prime is another code word which both happen to be close to w, then the distance between p and p prime is even smaller than delta, which is a contradiction. List decoding is sort of a generalization of this concept. It says, why stop yourself at delta by 2? Can you find me all code words which are within a larger ball around w, maybe a ball of radius delta times 1 minus epsilon? Well, in this case, we no longer have access to the combinatorial argument we just saw. So there will be a list of potential answers, all of which are valid code words, which will be within a ball of radius delta around w. And this is the concept of list decoding. So let us now try to understand the combinatorics of list decoding. First, let us see what is feasible. So there is this very popular bound known as the Johnson bound or the Johnson radius, which says that given an arbitrary center w, if we list all the code words which are within a ball of 1 minus square root 1 minus delta around the received word w, then this list will be small. And this is a purely combinatorial argument, but at least we can hope to algorithmically do something about it, since we a priori know that the list is small. On the other hand, if we try to extend this ball beyond 1 minus rate, or in case of MDS codes where 1 minus rate is the distance, or these codes meet the singleton bound. If we try to extend this ball around W to be more than delta plus epsilon, then we have no hope of doing anything, since there will be centers around which this ball will contain exponentially many coordinates. So one can ask, fine, what about the threshold? What if we are just a little shy of 1 minus rate or delta minus epsilon if you are working with MDS codes? Well, codes where the list still remains small or polynomial, even though you are arbitrarily close to the distance or 1 minus rate of the code, are codes which are said to achieve this list decoding capacity. And in some sense, they are very tight with respect to list decoding because we know we won't be able to do anything better. And of course, this is just a combinatorial question, and one can always ask the algorithmic question. If a code achieves the list decoding capacity, can you further efficiently find this list? In such a case, the code is said to efficiently list decode up to capacity, and the folded read-Solomon codes, multiplicity codes, the additive folded read-Solomon codes we saw on the first slide or the second slide are examples of codes which are efficiently list decodable up to capacity. Moving on, let us look at the attempt we give to capture all these codes. We do this via the concept of polynomial ideal codes, which is not entirely new to our work. It was already mentioned in the work of Guruswami Sahai and Sudan, but we give an abstraction of it which is useful to capture these codes. For that, we will consider a bivariate polynomial exy in the two variables x and y over the field f in such a way that the x degree of E is exactly S, and further the polynomial is monic in S, so the coefficient sticking along with x power S is just 1. And we will consider an arbitrary set S of n evaluation points in the field, and it is promised to us that if we actually substitute for y the various evaluation points, the various univariate polynomials that you get are all pairwise coprime. In a moment we will see examples where all these definitions will be clear, but let us for now see how do we encode a message polynomial p of degree at most k, or in fact degree strictly less than k, which is what f less than kx stands for, using this bivariate polynomial exy. So we take this polynomial px, which is our message polynomial, and we encode it by spitting out at each evaluation point ai the remainder of px when divided by exai. So px is a polynomial of degree less than k. When divided by a polynomial of degree s, it will spit out a polynomial of degree at most s minus 1. So the degree of this object will be most s minus 1. So it can be encoded by specifying s coefficients. So actually the encoding here can be thought of as residing in fqs or fs. If this field f is fq, then you can think of this object residing in fqs, and the entire code hence resides in fqs. So it is a block length n code, but the alphabet is now fqs. So let's look at examples of codes which we saw previously as polynomial ideal codes. So the most famous family is the Reed-Solomon family of codes. Here it's pretty easy to see how they are polynomial ideal codes. So we will define exy to be just x minus y. So s is 1 in this case, and we have the set of evaluation points a1 to an. Usually we are specified the evaluation of the polynomial p, of the message polynomial p, at the various locations in the Reed-Solomon codes, but that is the same as giving px mod exai, because exai is just x minus ai. So the remainder of px mod x minus ai will just be the evaluation of p at ai. Let's look at the next family of codes we saw, the folded Reed-Solomon codes with folding parameter s. So what these codes typically do is that at a particular location a1, let's say, you not only give the evaluation of p at a1, but you also give the translates, multiplicative translates of p by gamma, where gamma is a generator of the field, and so on and so forth. And you do the same for a different evaluation point a2, and of course you have the property that these multiplicative translates of a1 never intersects the multiplicative translates of a2, and so on up till an, which can be easily arranged for by choosing these points appropriately in the field. But one immediately notices that giving this information of pa1, p gamma a1, p gamma square a1 is the same as giving px mod the ideal x minus a1, x minus gamma a1 all the way up to x minus gamma s minus 1 a1. This is just a consequence of the Chinese remainder theorem, and hence the folded Reed-Solomon codes can be thought of as polynomial ideal codes where the bivariate polynomial representing them is given by this product of linear forms, all translated by gamma, multiplicatively translated by gamma. So let's move on, and now let's see the other popular family of codes called multiplicity codes with s minus 1 derivatives. How are these polynomial ideal codes? So in this case, the bivariate polynomial happens to be just x minus y power s, and again at a location ai, or let's say a1, you not only give the derivative, but you also give the the evaluation, but you also give the first derivative, and so on up till the order s minus 1th derivative of the polynomial, and you do this for all the endpoints. And just by a simple Taylor expansion around ai, we will realize that specifying all the s minus 1 derivatives along with the evaluation of the polynomial is the same as specifying the remainder of px when divided by x minus ai power s. Hence, multiplicity codes are also polynomial ideal codes. And now let's look at the lesser known family of codes known as additive folded Reed-Solomon codes, where instead of having multiplicative shifts by gamma, we have additive shifts by a different field constant beta. So at a particular location a1, you are not only given the evaluation of a polynomial, but also the various additive shifts of the evaluation point, and so on. And now again, by the Chinese remainder theorem, if you give all these pieces of information at the evaluation point a1, it is the same as giving the polynomial px mod this ideal x minus a1, x minus a1 plus beta, and so on up till x minus a1 plus s minus 1 beta. And notice that we will always need these evaluation points to be such that these additive translates of a1 do not intersect the additive translates of a2, and so on. And this helps ensure that these ideals ex a1, ex a2, ex a3, and so on are actually relatively prime. And this was also the case with the multiplicative folded Reed-Solomon codes we just saw a slide back. So it's really nice that we have been able to capture these codes using polynomial ideal codes. But does this help us explain this bundling in an algebraic way? Is there a common generalization of all these codes? Well, it turns out that yes, there is. And these are codes we define in our work, and we call them affine folded Reed-Solomon codes for obvious reasons, as we will see. And the bivariate polynomial in this case is given by a linear form L, where L of y denotes alpha y plus beta, and alpha is a non-zero field constant and beta is another field constant. And what we are going to do for the bivariate polynomial is have a product of s linear forms. The first linear form will just be x minus y, because L power 0 y is just identity, and L power jy just stands for the j iterations of L applied to y. So for instance, L square y would just be alpha square y plus alpha beta plus beta. And the bivariate polynomial is nothing but repeated applications of L to y s minus 1 times. And the set of evaluation points is again a1 to an, chosen appropriately so that these exy's are relatively prime. and you just as usual give the remainder of px mod exai. So again this remainder will be a degree s minus 1 polynomial, and hence it will reside in fqs. So let's look at how these codes are able to capture the codes we just studied. So let's look at one example where alpha is set to be gamma, the generator of fq star, and beta is set to be 0. In this case, the ideal you will get would just be x minus y, x minus gamma y, so on up till x minus gamma s minus 1y. It will just keep on multiplying, and hence this just forms the FRS family of codes. Great. Uh, Now let's look at how do we get additive FRS codes. So for that we will set alpha to be 1 and beta to be some non-zero constant, in which case the bivariate polynomial will just become x minus y plus beta, and so on and so forth up till s minus 1 times beta, which is exactly the bivariate polynomial we saw for additive FRS codes. And also these codes capture multiplicity codes. How do they capture multiplicity codes? So for that we will set alpha to be 1 and beta to be 0, and then the ideal we'll get is just x minus y power s, which is exactly what we just saw. But interestingly, they capture other codes which are an inherent combination of FRS and multiplicity codes. For instance, if we set alpha to be minus 1 and beta to be 0, we will get the ideal x minus y power s by 2 and x plus y power s by 2. I am assuming s is a even integer. So even these codes are captured in our definition, and as we will later see that whatever we know about list decoding for FRS multiplicity codes is also true for such codes. So what are our results? Firstly, we show that every polynomial ideal code, whether or not it is given in this affine way, is list decodable up to the Johnson radius. This more or less follows the outline of Guruswami Sahai Sudan, but there are some steps which were missing, and we flesh out those steps. And more importantly, we show that all known codes which achieve the list decoding capacity can be captured by this one single statement that affine folded Reed-Solomon codes achieve the list decoding capacity under some conditions, where either the order of this linear form, which means how many times do we have to iterate before getting back the identity, is large, or the characteristic of the underlying field is large. And these assumptions are not just artifacts of a proof. There are very good reasons for these assumptions, because it is possible to otherwise embed the Reed-Solomon codes into these folded codes, and if you could list decode them to the capacity, in particular you would be able to list decode Reed-Solomon codes beyond the Johnson bound, which is still a big open question. And the main punchline is that we can abstract whatever we know about folding and bundling into this nice algebraic family of codes known as affine folded Reed-Solomon codes, and they seem to capture the different, at least on the surface of it, the different codes like FRS, multiplicity codes, and additive folded Reed-Solomon codes. Now we will present a different view of polynomial ideal codes, which is very helpful in abstracting out their list decoding properties. And we will not go into how this view is helpful, but we will just try to understand why this nice linear operator like view of polynomial ideal codes exists. So let us say we are given a bunch of linear operators, s of them, and these are linear operators from the polynomial ring fx to the polynomial ring fx. So it takes a polynomial p in fx and spits out another polynomial, and we are again given an evaluation point, a set of evaluation points a1 to an. The encoding of a message polynomial p of degree less than k is then given by just applying these linear operators to the polynomial p, getting another polynomial, and then evaluating that polynomial at ai. So again, this will be a member of fq, and hence overall the alphabet becomes fqs, right? So it's a very simple definition. It just takes the S linear operators, applies it to the polynomial, and just evaluates it at the evaluation points. So let us now look at some example of linear operator codes and see how they tie up to previous codes we saw. So the first is the Reed-Solomon family of codes. Well, here the linear operator is just the identity operator, and this collection is nothing but just the identity operator, since here there is no folding, so S is just 1, and that is indeed the case that at a point, whether we give P AI or the identity operator applied to P evaluated at AI, it's the same thing. The next interesting family is the folded Reed-Solomon codes. Well, here the linear operator does a little bit more. It takes a polynomial P and spits out the polynomial, which is a multiplicative translate by gamma. And indeed, the collection of operators is given by just various iterations of this one operator. And if at an evaluation point we give PA, P gamma A, and so on, it is the same as at giving the linear operator code specified by L, simply because Li P evaluated at A is nothing but P gamma I A. For the multiplicity codes, the linear operator L is, as you would have guessed it, just the derivative operator, and indeed the collection is nothing but various iterates of this operator. So the s minus 1th operator is just taking s minus 1 derivatives, and indeed at a location we specify p, the various derivatives of p, which is the same as just applying the operator to p and then evaluating it. Similarly, for the additive FRS codes, in this case this linear operator is given by just an additive shift, and pretty much the same thing happens. The collection is just an iteration of the same operator. I'll leave you to figure out the equivalence of additive FRS codes this way. And the affine FRS codes are a little more interesting in this sense. I won't give you the general description, but let's just try and see what happens for this specific code which is not covered by the previous examples. So firstly, when we want to go mod this bivariate ideal at the evaluation point A, let's say, okay, that is the same as going mod this polynomial, which is the same as specifying not only the evaluation of P at A, but the evaluation of its derivative at A, the evaluation of its s by 2 derivatives at A, and the evaluation of P at minus A, is derivative at minus A, and the s by 2 derivative at minus A, or rather s by 2 minus 1, which is the same as using the following set of linear operators. So the linear operator L, which is given by the derivative, and a different linear operator L tilde, which differentiates the polynomial but evaluates it at minus x. And you can see that this piece of information is just the same as the following piece of information, quite literally, where again LIP is just the iteration of this linear operator, and on this side we will have L tilde, the operator L tilde instead of L. So in general, affine FRS codes can be interpreted as linear operator codes. There is something more than that. The linear operator codes we saw in the previous slide are actually a very specific family of linear operator codes. They have this nice property of linear extendability. What this means is that if you are given this vector, by this notation I just mean this vector where you are given L0 px, L1 px, all the way up to ls minus 1 px, and you want to find out the vector which corresponds to the polynomial x times px. So this is another vector. Then this can be given by just multiplying a matrix mx where each entry is a polynomial, so it is a matrix in the formal variable x times this vector. And what we show in this paper is that linearly extendable codes defined this way are just the same as polynomial ideal codes. So let's see this definition in action to get a little bit more of an idea. But essentially this definition is saying that, okay, you give me this vector of L applied to P. I can multiply with the matrix Mx and give you the vector that you would obtain if you applied L to X times P. Okay. So let's see this definition in action on the previous code families. Well, for the Reed-Solomon codes, this is kind of trivial since there is only one linear operator, and that's the identity operator. For the folded Reed-Solomon codes, let's take the folding parameter to be 2 to get a better sense of what is going on. All we are saying is that if we look at the vector p x and p gamma x, which is what LP, script LP would look like, then there is a matrix which we can write, which would give us script L applied to x times px, which is just xpx and gamma x times p of gamma x. And notice that this is actually a diagonal matrix which does this. It's just x and gamma x. So yes, these codes are indeed linearly extendable, and this works for any s. For multiplicity codes, again, let's take s equal to 2 to get a bit of a feel. So here we want to say that the following can be related by a matrix: the derivative of px, and here we would just write x px, and the derivative, which is going to be by the product rule, xp prime x plus p. So as you can see here, the matrix would be the following, and yeah, so again, multiplicity codes are linearly extendable, and I will leave it to you to figure out how additive FRS codes and affine FRS codes fall under the same definition. There is yet another property of the linear operator codes we saw previously, and that property is that they are essentially getting generated by a single operator L and its various iterate. In particular, let us consider an L which is degree preserving. What does that mean? That means that it really behaves as a linear operator from polynomials of degree less than k to polynomials of degree less than k. That is, if it takes a polynomial p whose degree is something, then the image of the linear operator L when applied to p will have degree not more than the degree of p itself. So such operators are called degree preserving, and hence this linear operator L can really be thought of as a k cross k matrix, where it takes in the coefficients of p, a polynomial degree less than k, and spits out another polynomial of degree less than k. And if we collect various iterates of this polynomial and they happen to form a linearly extendable family, then such a code will be called an iterative family of linear operator code. And we will now concentrate on an object which will be useful to state our results, which is this object called diag_L, which is nothing but a collection of the diagonals of these various linear operators L0, L1, and so on. So you look at the operator L0, look at its diagonal and just stack it up as a column. Similarly for L1 and so on. So if you look at this object, this diag_L object, it is another generator matrix of a code, and the distance of this code happens to capture the list decoding properties of all the codes we have seen till now. In particular, if the distance of this code is k minus r, then the linear operator code corresponding to script L is efficiently list decodable up to capacity with size mod f to the r. And our proof is based on an abstraction of Guruswami Wang, basically realizing that it applies to a much more general class of codes rather than some ad hoc arguments for multiplicative codes, folded read Solomon, additive folded read Solomon, etc. And with that, we were able to conclude that a fine folded read Solomon codes can achieve list decoding capacity efficiently under some constraints. And I thank you for your attention.